Today we will hear about bizarre one-dimensional quantum world and maybe a few very brief kind of organizational things. So the talk is going to be recorded, and I specifically organize this event not as a webinar, so people can switch on videos and we can try maybe to create a bit more interactive environment. Please still stay on mute, right? But everybody is welcome to switch on their videos, and because it's a webinar, in principle, people are also allowed to unmute, but I propose that in the question session, people write in chat, and I announce the order in which questions are going to be asked, just to, to avoid unnecessary interference and some potential side effects. And with this, I guess it's a great pleasure. And we are looking forward to the talk.
Thank you, Maxime. Can you hear me well? No mic problem? Okay, super. So good afternoon. Thanks to all for being here. And of course, a special thanks to Maxime for inviting me to give this colloquium and also organizing a nice virtual visit of the Institute. It's, of course, I regret deeply not being able to be there in 3 dimensions, but okay, at least the 2-dimensional visit was extremely pleasant. So it's my pleasure to tell you about the bizarre one-dimensional quantum world. It's a field which I love, and I know that Maxime told you to wait perhaps the question session for asking questions, but I would say if there is something that I'm saying which is really not clear or which you would really have an urgent question, don't hesitate to put it in the chat or wave your hands. I'm not seeing all of you on the screen, but since this is a colloquium, it should be accessible, and so don't hesitate to ask a question if you have a pressing question. Okay, if you want to know more, here is the link of the group where you can find more details on the activities we are having in the group. Here are the various sponsors which contributed to finance not what I'm going to tell you necessarily, because what I'm going to tell you will cover much more than what was done in our own group, but certainly the research which was done in the group. Here is a view of the group as of March of this year. As you can see, we were in confinement at the time in Geneva, so this is a slightly unusual group picture, but we could not resist at the time to take a group picture reflecting the situation that we had at the moment. And besides and beyond the group, I of course benefited from many interesting and crucial collaborations and discussions, both on the side of quantum matter in what I will tell later on spin systems, both on theory and experimental side, and also we had very strong interactions on cold atoms. Again, many theorists, many experimental groups. There are too many to be able to be all mentioned there and thanked there, but they really contributed to our understanding of this one-dimensional world that I'm going to tell you about. Okay, so let's fasten seatbelts and let's go. And let me move a little bit backward and discuss on how to master materials. And you know that materials are extremely important for humanity, and that's simply obvious because they are all ages of humanity which have been named after a single material. You get the Copper Age or the Bronze Age and so on. And it's not so easy to master materials. If I had to, by the way, give a name to the 20th century, it would be definitely the Silicon Age, because otherwise we would not be even able to have this conversation. What the 21st century will be, I don't know, but we'll see. So if you look a little bit at your 101 theory course on materials or on solid state, what you understand pretty well are free electrons. You've been all fed up with free electron theory. But actually, if you look at real systems, even simple materials like aluminum, the Coulomb interaction inside these systems is humongous. And it's the same order than the kinetic energy of the particle, and it's of the order of 10,000 Kelvin, which is 1 electron volt roughly, which means that all these effects are important at room temperature. A solid, your cell phone is quantum mechanics you can touch, essentially. But also it tells you that normally in a real system, you should never be able to neglect the interaction, even for the most basic metal. So if we just have to deal with the interaction, normally we would be sunk, because this is a terribly complicated problem. 10 to the 23 particles, more than stars in a universe, essentially, interacting all together via, for example, Coulomb interaction in a solid. But we were extremely fortunate to discuss realistic solid state system, that there was a theory which was existing and put by Lev Landau, which is called Fermi liquid theory, which in short says, when you have fermions, by using the Pauli principle and a little bit of magic that Landau knew how to do, you can completely forget about interaction at the price to redefine some parameters of the system, like the mass of the particle is now renormalized by interaction. But for the rest, you can look at the system as free particles. And this was a fantastic success, because it allowed to use this simple theory of free electrons that we had from quantum mechanics to describe solids, to describe materials. You knew why some materials were metallic, why some were insulating, why some were semiconducting, and this allowed to do fantastic things. Understanding what semiconductors are allows you to get the transistor, and then here is one Nobel Prize which was attributed for this. Understanding how free particles can interact with the tiny vibrations of the lattice allows you to understand superconductivity, and this was the famous Bardeen-Cooper-Schrieffer theory, and this caused a string of Nobel Prizes due to this fantastic discovery in fundamental science. Closer to us, understanding how free particles move in magnetic fields allow you to understand why the transport property, the resistance of these materials, can be strongly affected by magnetic field, and it's called the giant magnetoresistance, which was the Nobel Prize of Fert and Grunberg, and was the starting point of something called spintronic that was discovered. Now, I've mentioned these discoveries here, all rooted in Landau Fermi liquid theory, not only because, as you see, they are fundamental discoveries that completely reshaped our understanding of the world at the level of fundamental physics, but also because they completely changed our world, the way we know it. The transistor has, of course, completely shaped the information society in which we live. And again, without transistor, I would have to completely renounce on the visit of the Institute. Superconductivity is operational. Every MRI magnet in an hospital is essentially a superconducting magnet. So you see it less obviously, but it's already in your lives. And giant magnetoresistance caused a complete revolution in magnetic recording and allowed to miniaturize devices to a level that was thought impossible before. So all these discoveries have shaped completely the 20th century world, essentially. Now we are facing a new challenge, which is to continue to harness materials and to harness the materials of the future, which will, for example, harvest heat to produce electricity, or harvest light to produce electricity, or vice versa. And for that, it's very hard to imagine that to do this, which will involve the spin, the charge, and the orbital properties of the material, that we can do this by playing at random with a periodic table, and that we can do it without understanding interaction. So Landau bought us 50 or 60 years of time, but now we have to face the music and we have to really understand interactions. And that's an horrendous problem. Again, 10 to the 23 quantum particles, and I remind you that wave function needs to be totally anti-symmetrized or symmetrized if it's bosons, which means that even free particles are not easy. But if you add interaction among them, it's not just that you get more equations and whatever, it becomes a problem which so far even the most powerful computers are unable to treat, and that analytically are extremely, let's say, resistant to theorists. So we really have to go beyond what we are able to do and being able to tackle this problem. So this is, of course, a humongous problem, and I will not deal with this. But among all these problems of interactions that exist, one is, I would say, especially funny, at least beauty is in the eyes of the beholder, is especially funny. And that's what happens when there is objects which have very small number of dimensions. Now, this is not just an ideal occupation, because if you look at what happens in future electronics, you notice that, of course, the number of objects that are integrated on one circuit is growing like crazy, and therefore the size of the objects are decreasing like crazy, which means you really have to shift the study of that was the main focus maybe in the mid 20th century of studying big bulk crystals, 3D and whatever, to studying objects in reduced dimension, films, lines, and so on and so forth. So that's a very practical reason to worry about reduced dimensionality. And reduced dimensionality might be films, might be lines, and so on. But of course, that's not the only reason. The other reason is that this physics in reduced dimension, and in particular physics on lines, on objects which are one-dimensional, carries really new concepts and new physics that was not existing before. And I think the first time this really appeared to the face of the physicist in its full glory was when people looked at the quantum Hall effect. And this was made very, very apparent by Bert Alprin, where you see that the Landau levels, the levels of energy of the particles in a solid are deep inside the material, but at the edge of the material, they cross here the chemical potential, which means that all the physics of the system is actually controlled by edge modes, which only exist at the edge, the physical edge of the material, and which completely carry the current in the system. And this has been even more evident recently when people looked at something called topological insulators or something called the quantum spin Hall effect, where in these materials, although the material is bulky, is two-dimensional, most of the physics is controlled by channel of conducting particles which are moving at the edge. And this made the physics of these edges particularly interesting to study. Okay, now one-dimensional quantum system from the point of view of a theorist also is a beautiful thing to study, not just because it has applications or because someone can do a device with it. And the reason is that it's the dimension in which the material is the further removed from what you would expect in, quote, high dimension. Let me explain. If you take particles in 2 dimensions and you say they have the strongest interaction I can think of, hardcore repulsion at a certain distance, at the end, they behave a little bit like free particles. Look at this particle here. It can just ignore the other and just move here, just like if it was a free particle. So even in 2 and a fortiori in 3 dimensions, even if the interactions are very strong, at the end, they might have very little effect. In 1D, it's not at all like this, as anybody who has queued in a cafeteria or a movie theater knows. If you have interactions, then you cannot pass the person who is in front of you, you cannot pass the person who is in front, and so on. So every individual motion has to be transformed into a collective motion of the particles. And that's unique to 1D. If you're in more than 1D, you can recover your individuality. Another example of this is when you drive a car. If you had only a single lane, you cannot be an individual. You have to move as a wave together with all the other cars. If you have more than one lane, you can pass and zoom and recover your behavior of a single particle. So 1D is the dimension in which you can expect even small interactions to have big effects. And that's, of course, especially interesting. On the point of view of methods that we use, we are used to the fact that usually we deal with mean field methods where we say, oh, there is some kind of order, and we assume the order is existing, and then we deal with small deviations to this order. For example, if you have a wave function, you can say, oh, I have the phase of the wave function, which is well ordered, and it's Bose-Einstein condensation. And then you deal with small fluctuations of this phase. In 1D, there are theorems which tell you that whether it's due to quantum fluctuations or thermal fluctuations, the fluctuations are strong, and they will destroy this type of long-range order. So all the methods that we know and love of mean field theory and so on that we used in more than one dimension, we can take and put directly in the wastebasket. And we need to invent new methods to deal with one-dimensional systems. So this difficulty to order is something which is also extremely interesting to tackle in one dimension. So all this makes the one-dimensional quantum world particularly fun to study. And I would like to take you today into a tour of this one-dimensional quantum world. So this is a beautiful theoretical problem. Of course, it's not a new problem, but it's a problem that has known huge progress in the last 15 years. And both because of the experimental situation that has evolved, but also because of theory situation that has evolved. So let me just give you a very brief historical tour. Initially, this problem was tackled by people like Tomonaga-Luttinger, and then by the Russian school. Here you have Lev Gorkov, Igor Dzyalujinsky, Anatoly Larkin, one of my heroes, where they took this problem as a standard many-body theory problem and went at it with Feynman diagrams and Parquet approximation, and they obtained an incredible wealth of results. But clearly, they also established that this is not the good method to tackle this problem. This problem is very resistant to what I would call standard many-body theory. Then, in parallel, came beautiful exact solution, deep reaching solution from Hans Bethe, which is called now Bethe-Ansatz. And let me show you here Hans Bethe and Elliott Lieb, who was one of the main players in this game. There are, of course, many others, but he was definitely one of the person who obtained many of the solutions. And that's the fantastic thing, that in one dimension, you can solve exactly a problem. Of course, very often solving exactly means you can prove that the solution exists, period. A little bit more, you can write equation for a finite number of particles, and then you need to numerically solve the equations. Or a little bit more, you can do the thermodynamics. But it's very difficult with this method to deal with correlation functions, to compute really what is going on in the system. And that was definitely one of the breakthrough of the I would say recent years, that now the Bethe-Ansatz community is also able, for very limited set of models, to compute also some correlations. Then you have field theories, so-called bosonization method, which I will not discuss, but which is the sort of standard method to deal with 1D system, and conformal field theory. And there many people played a role, but probably the three main players are Alan Luther, the late Vic Emery, and Duncan Haldane, that I'm sure everybody knows, who did extremely deep contributions in the 1D world. And these theories are nice, but they only describe the system at large length scales and low energies. And if you want things at short length scale, high energy, you're dead. You cannot use this method. Of course, the better ansatz solution potentially can give you this. And closer to us, there was a fantastic development in numerics. There are many numerical methods, but the main method that has made a lot to make progress in 1D is so-called DMRG, Density Matrix Renormalization Group, which was invented by Steve White, and which is really a killer method in 1 dimension, because it allows not only to compute static correlation functions, but also dynamics out of equilibrium situations. But the numerics is valid at short distance, not too long system, not too low energy. And so the thing which allowed to make humongous progress in the last 15 years is that people have learned how to make these three methods, which are totally complementary, work together. And if you have a take-home message to take, and you're a theorist, is that one of the reasons why 1D systems have known so much progress in the last 15 years is not because everything was solved by field theory, or everything was solved by numerics, or everything was solved by better ansatz, but that people knew how to make these three things work on the same problem together. And that allowed to use each technique in the region where it was strong. Numerics at short distance, high energy, field theory, but with some inputs from the numerics at large distance, low energy, and better ansatz, either as a way to benchmark numerics or field theories, or as a way to provide input to the field theory for the regions that were beyond, or the quantities that were beyond the better ansatz. So I think it's a real success story. And if we were able to do this in 2D or 3D, I'm sure many, many problems would simply crack the way they have cracked in 1D. Okay, so much for the historical part. I will not go in details, of course, in the calculations. I will follow the method which is then a miracle occurs, and I will not tell you how to do practically calculations, but if you want to know more, here is the list of references where you can find details, of course, on this 1D physics and the technology to solve it. This one is probably the most accessible and short, and then it goes into more complex things. Okay, so let me tell you a little bit what is the remarkable physics that many 1D systems share. And again, it's not all 1D systems, but it's many of them. It's called Tomonaga-Luttinger liquid, and it kind of replaces the Fermi liquid theory in 1 dimension. So we have our own little universal theory, the same that Landau had for all solids, but for all solids or most solids in 1 dimension. First, as I said, there is no individual excitation. Everything is collective excitation. So these excitation are kind of sound waves of matter with a given velocity u. And the system doesn't know really where to order or not order. So most correlation functions decay as power laws. And what is remarkable is that all this power law decay of all the physical quantities only depend on one number, which you can compute, which is called the Luttinger parameter, and which people usually denote by the letter K. So you get something which is incredible, that the same way that Landau told you, you can ignore interaction and replace the mass by a renormalized mass. I'm telling you, if you know two numbers, you can completely characterize your system. And for example, let me give you for bosons the correlation function. So I create a boson at point 0, and I try to destroy it at point x. And you see that the amplitude of this quantum mechanical process decreases as a power law as 1 over x. and with an exponent which is fixed by this parameter k. If I want to look at fluctuations of density, I create a density ripple at point 0, and I want to see if the density ripple exists at point x. Again, to cut a long story short, it decays as a power law with an exponent, which is again a function of this parameter k, but this time with a different functional form. So this is a kind of behavior that normally in higher dimension you would associate with a critical point, with a point where you are right at the phase transition. And because of this, of course, many 1D systems will have extremely peculiar properties, because it's like if they are poised at the brink of an instability. There is another property which is quite remarkable and quite unusual. It's called the fractionalization of excitations. Now, we are used into the fact that when we agglomerate particles, we get quantum numbers that are bigger than the individual quantum number of an excitation. A nucleus has a charge which is a multiple of the charge of the proton, and it's a bound state of many, many protons. Now, in 1D, it's exactly the opposite that happens. You can get excitations which have quantum numbers which are smaller than the numbers of the individual excitation. Let me illustrate it here with an Heisenberg spin chain, which I can represent as spin up, down, up, down, up, down, up, down. And now I create the minimum excitation I can do in this system. I flip a spin. So I flipped a spin plus 1/2 into a spin minus 1/2. So this excitation has a spin -1, quantum number delta S equal -1. And if you were in 3D, this excitation has a very well-defined relation between its momentum. Okay, here I created at one point, but its momentum and its energy. And it's called a magnon. It's called a magnetic excitation, a magnon. Now in 1D, I can do the same thing. And if I want to have my magnon propagate, I will apply the Hamiltonian here, which contains term S plus, S minus, so which will flip the spins. So let's do it. I flip 2 spins here. I flip 2 spins here. I apply the Hamiltonian again. I flip spins. And now you see my magnon has completely disappeared. This place where I got 3 spin down together has disappeared, but has been replaced by 2 places where there are 2 spin down, which are close together. These 2 excitations, which are topological in nature, because you see they are surrounded by a string of turned particles here, are called spin-ons, and they carry actually a spin 1/2. So it's like if the magnon has broken into 2 spin 1/2 excitations, which would simply not exist outside the 1D world. And these excitations are non-local and topological in nature. Here is a spin-on, a single spin-on. And of course, as physical objects, they can only be created by pairs, because again, if you wanted to create one single spin-on, you would need to turn the spins on the chain on all the sides up to infinity. It also tells you that in 1D, you very often have hidden topological order parameter, and that's one of the most exciting features of 1D. You can study phases which have very nice topological properties, and this is an ongoing, very active branch of research that I don't want to comment too much on it, but I'm just pointing out that in 1D, of course, topology is the rule rather than the exception. It also tells you, because you've broken your magnon into 2 excitations, that you can spread the momentum between these 2 excitations the way you want, and therefore the energy of the excitation will be the sum of the energies, which means there is not anymore a well-defined dispersion between momentum and energy. So instead of having a nice particle, you now get a continuum of excitations. And this continuum of excitation will lead to decay, will lead to a certain number of nasty properties that are very, very interesting. This has a name. This is called the de Cloizeau and Pearson spectrum, but let me not discuss. You can even get more bizarre effect, and I don't want to spend too much on it, but if you have objects which have spin, like electrons, what happens with a magnon can also happen between the charge and the spin. Let me remove an object which carry a charge and a spin, which is the electron. And now let's have this thing evolve. I flip the spin just like before, and you see that my spin excitation is moving away. and is reaching a place where no charge is missing. But I have my spin-on here. On the other hand, I can decide to move particles. If I move particles, you see that the spin arrangement remains the same, down, up, down, up, down. And of course, there are more serious calculations than what I'm showing you with these little cartoons to study this. But then you have a region here where the magnetic environment is up, down, up, down, up, down. So no spin is missing, but a charge is missing. This excitation is called a holon. It's a hole, if you want. So in one dimension, you can deconfine an electron into a spin-on and a holon, which will have deep consequences, because if the particle needs to be put back in another chain or extracted from the system, it has to recombine. And this, of course, is not easy because the excitations can go where they want. Okay, so this is a little tour of the typical 1D physics that we have. And that's super interesting, but does it exist? And of course, you could imagine that this is a pure view of the theories. So I've given you here two references which discuss experimental consequences a little bit more in details. And of course, the answer is yes, it does exist. In condensed matter, one of the first example was provided by organic conductors, synthesized by this gentleman, Klaus Beckgaard, and measured by this other gentleman, Denis Jérôme. And these are stacks of molecules where the overlap of the atomic orbital is essentially perpendicular to the screen. So the conduction is excellent along the stack and very poor between the stacks. So although the material is bulk 3D, the electronic properties of this material is really many, many uncoupled or weakly coupled 1D chains. And these materials, by the way, we still don't understand really how they work, are superconductors with a mechanism we don't understand, with a very low TC of the order of 1 Kelvin, but they have an unknown superconducting mechanism. So in that category, they are like the cuprates, like the high TC. But because they are made of this one-dimensional chain, they also show this bizarre power law physics that I was mentioning. And this was probed for the first time, to the best of my knowledge, by the group of George Gruner, Leo De Giorgi, and Martin Dressel, using optical conductivity. So here is a plot of the frequency-dependent conductivity of this material. You see that there is this tail here. And lo and behold, if you compare with calculations using this Tomonaga-Luttinger liquid physics, you find that you expect a power law, and you do see the power law. So this was, to the best of my knowledge, the first observation of Tomonaga-Luttinger liquid physics in an electronic system. But of course, you would like more, but at least you see this very nice power law absorption. The fractionalization has also been observed. It's a very difficult experiment and very elusive in condensed matter. And it has been observed in experiments done by Amir Yacobi then at the Weizmann and then at Harvard. And the theory was made by Bert Alprin and Cherkovniak. And this is in another experimental system which uses semiconducting wires, which are so small that they can be assimilated to quantum wires due to the transverse quantization. And the idea is that they do a kind of interference experiment where one particle tunnels here, then separates into spin-on and holon, then is extracted here by the contacts. And because these two objects have two different velocities, you should see in the tunneling experiment two lines in the spectrum, which is not totally obvious here. And therefore, you can do a moire pattern experiment that is coming from the two velocities that this object have. So just to show that these theoretical predictions can be reasonably well observed. More recently, one could even do quantitative tests of the Tomonaga-Luttinger liquid theory. I don't want to go into details, but the best systems to do this are quantum spin systems. These are wonderful systems which you can find in a series of groups. Here was a group of Claude Berthier in Grenoble, where you get these ladders made of copper sides which carry a spin 1/2 here. And this spin 1/2 can be magnetized by application of a magnetic field. And because of the ladder nature of the system here, the system is one-dimensional and obey Luttinger liquid theory. The compound, like the organic conductors, is bulk 3D, but there is very little magnetic exchange between this ladder and this ladder, and therefore you can consider that this is made of independent chains. I will not go into details of what exactly is measured. It's the so-called NMR relaxation time, just to show you that one can do a theory of it. Here is a formula where all these parameters are known from the microscopic Hamiltonian of the system. The exchange, the magnetic exchange, gives you what should be K, what should be U. This is the temperature, and so on and so forth. And therefore, there is not a single adjustable parameter in this curve. Here is the dots are the measured quantity from the group of Claude Berthier. This is Martin Klanczek who did the experiment. And the red curve is the theoretical calculation, which was done by Pierre Bouillot, who was at the time a graduate student in the group, and Corinna Collat, who was in the group at the time, is now faculty in Bonn. And you see that there is a fantastic agreement between the theory and the experiment. And this is something which for me is a kind of a miracle, because in condensed matter, we usually have something to adjust. We know the power, but we don't know the prefactor and so on. And just to show you the control we have on the theory here, we can fit essentially the experiment without adjustable parameters. So this theory is extremely successful. There are many other 1D systems, edge state in quantum Hall effect, photons in wave guides, topological superconductors, and of course I will not have time to discuss about them. There is another field of physics which helped tremendously to do progress in 1D understanding, and this is called atoms. As you know, atoms can be trapped, can be cooled using lasers. I think Vienna is the place where I don't need to explain this. If you use this, you can realize virtual solids. You can realize solids in which the periodic potential is imposed by light. The tunneling here is simply a neutral atom going from one of the minima here to the next, and you control this tunneling by the amplitude of the lattice. And because atoms are neutral, they only see each other when they are in the same well of the potential. So this is excellent realization of system with short-range interaction. And of course, the person and the group who proposed this to use cold atoms as virtual solid is Peter Zoller. And this is an incredibly successful proposal, which was beautifully tested by the Munich group, Markus Greiner, Tilman Esslinger, Immanuel Bloch, and Ted Hensch, in demonstrating that they could observe a metal insulator transition or superfluid insulator transition in bosons by varying the size of the lattice. So since then, this has been used tremendously to test and to make discovery on one-dimensional theory. This sounds too good to be true. You have excellent control on the model. You can control the interactions. You can control the statistics by loading your traps with either bosons, for example, lithium-7, or fermions, for example, lithium-6, which give you pretty different momentum distribution function. And you can control the dimensionality, because if you change the intensity of the periodic potential that you put, you slice the system either as 1D tubes if you put 2 periodic potential, or pancakes if you put only 1. So this is a very good set of systems. And indeed, people use this system as well to test Tomonaga-Luttinger liquids. So here in Vienna, there were beautiful experiments done by the group of Jörg Schmidtmeyer using atom chips, where by doing interferences between 2 condensate, he could probe these power law correlation functions that I was mentioning. And the theory was done by the late Adilet Imambekov, Vladimir Gritsev, and Eugene Demler. And lo and behold, this was fitting pretty well with what you would expect from Tomonaga-Luttinger liquid theory. For fermionic systems, one could also test this. This was, I will not go in details. This was done in the group of Randy Hewlett in Rice University, and we helped a little bit, in particular Piotr Grissins helped a little bit with the theory. And there, this was using a technique known as Bragg spectroscopy to measure the velocity of this excitation. This velocity that I was mentioning is the velocity of collective waves. And again, here is the agreement between the theory and experiment. The theory is the dashed line and the experiments are the dots, as a function of the strength of the interaction for the peak frequency, which is essentially the velocity. Okay, so yeah, which led some side to say ultra cold atoms confirm 50 years old physics theory. I don't know if it should be taken as a compliment or as an insult, but okay, that was a beautiful, beautiful experiment. So one has quantitative agreement with predictions of Luttinger liquid theory. So when you hear something like this, the natural reaction is to say, okay, that's okay, end of the story. Let's work on something else. There is nothing left to do. We move to, I don't know, 2D or 3D or whatever. But that's not correct. And of course, I don't want to leave you with this impression. I just want to tell you that now Luttinger liquid is playing the same role than Fermi liquid did. It provides the basis by which we can treat the interactions. And now we need to invent the semiconductors, the superconductivity, the giant magnetoresistance. So we need to take this field away from the simple, plain vanilla 1D chain and bring it to a place where we have, again, a challenge. And believe me, this is not what is missing. So in the remaining, 10 minutes that I have, I would like to boldly go where theorist has gone before and take you to some of the challenges that exist. And I don't think I need to do too many of them, but to show you that there are now, based on the top of Luttinger liquid theory, many, many challenges coming from the one-dimensional world for which one needs good experiments and one needs good theory, because we really don't understand what is going on. Beyond Luttinger liquids, you can add perturbation, a lattice, which will cause Mott transition. You can add disorder, which will be Bose glass or something called many-body localization, which I'm sure you heard a lot about in this institute. You can worry about multi-components, mixtures. All this do not obey the plain vanilla Luttinger liquid theory that I showed you. And for most of these things, we have no clue or very little clue of what is going on. You can study new type of quantum critical points. There are some of them which are deeply topological in nature because of the 1D structure. And as you know, topological preoccupation are something that is worthy of interest. Let me show you one example. 1D bosons plus a lattice. It's mappable on the sine-Gordon Hamiltonian, which is an Hamiltonian which by itself is pretty well studied. And there, it's something that shows a Berezinski-Kosterlitz-Tarless transition. So a very, very nice form of transition, for which these two gentlemen got the Nobel Prize in 2016. And again, cold atoms have provided fantastic laboratory to study this. I don't want to go into the details, but there were very beautiful experiments in the group of Hans Christoph Nagel in Innsbruck, where he was studying bosons with a weak lattice on the top of it, which are described by this sine-Gordon theory. And he was studying the superfluid to Mott transition that occurs in such a system. And by looking on how this transition evolves with the strength of the interaction, you show that there is a magic strength of the interaction below which even an infinitesimally weak lattice is able to give you a Mott insulator, which is very specific to 1D. And this magic value here is described by the universal behavior of a BKT transition. It was not possible in his experiment to really pinpoint this transition. This was done in a more refined experiment by Giovanni Modugno in Florence, and Laurent Sanchez Palencia and his group and my group helped a little bit for the theory. And when you do this, you find this magic point here, and you can check that this is indeed the universal value that the BKT theory provides. So actually, these 1D quantum systems are probably one of the best way to test for the BKT transition, which was initially proposed for 2D classical systems. So this is one remarkable set of things. Let me skip the topological order. I don't want to spend too much time in it. Out of equilibrium situation, that's a place where the theorist is extremely defenseless. We are good when we have Boltzmann factor, but we are not so good when we need to deal with situations which are out of equilibrium. Let me show you a couple of situations like this, which are occurring in 1D and are very special in 1D, and which both the experiments in cold atoms for which the experiments in cold atoms helped us to make progress in our thinking on this. Let me take a chain of particles, which can move, of course. They are quantum bosons, let's say, with interactions. And now I transform one of the particle into another species. So I have one ugly duck here, which is moving in the bath of all these other particles. And of course, all these particles are interacting between them, and this particle is interacting with the particle of the bath. Now, the question is, how does the contact with the bath is impairing the motion of this particle? And we know this problem classically. It's called Brownian motion. And we know that normally it leads to diffusion of the particle. It leads to a motion of the particle whose position grows from the square root of the time. Now, what happens if we have a quantum bath in 1D? Well, the particle will move elsewhere and we need to measure it there. And this is a problem we looked a couple of years ago with Misha Zvonarev, Vadim Sheyanov. And one of the big surprise that the simple calculation we could do is that instead of diffusion, you got subdiffusion. You got that the position of the particle as a function of time was not square root of the time, but was log of the time. So this was way worse than what we can expect out of a diffusive particle, and even worse than what you would think if you were applying Fermi liquid theory to this, saying, oh, I need to renormalize the mass. Because of the other particles, this particle has now a renormalized mass, and then it moving ballistically with a renormalized mass. So this is a mess. This theory is far from being complete. There are many, many other works. I've shown a couple of those. And just to flash two experiments, which helped a lot. One was done in Florence, and this was a light blade confining potassium atom in a rubidium C of quantum particles. So you release the blade, you extinguish the laser, and then you follow the potassium atom. And the other was done in the group of Immanuel Bloch using a quantum microscope, where you only see here the red particles. You don't see the other particles along each line. And this is the quantum horse race, where you put all these particles at the origin at time 0, and then you release them and you let them move. And this type of experiments allows you to describe quantitatively what is going on with this very complicated out of equilibrium situation. Quantum transport. In condensed matter, we are so used in measuring resistance that we forget how important this is. And very recently, the cold atom people have managed to produce devices, in particular in the group of Jean-Philippe Brantu and Tilman Esslinger, where they can realize an experiment that one does routinely, I would say, in a solid, which is to take a reservoir here of particle, have a channel here injecting particles and measuring them in the other reservoir. So you put a voltage difference, there is a current going through, and you put obstacles here to prevent this particle from moving. And this is just one example of an experiment where a 1D periodic lattice has been superimposed here. And the question is, if I have superconducting reservoirs, so particles which are pairs, do they move or not through this channel? And the naive idea would be to say, yes, it's a superconductor. They should flow very freely. And the experiment is telling the contrary. If you have non-interacting particles here as a function of the gate potential, which tells you the density of particles in the channel, Here is the conductance. You see, you get a certain curve. It doesn't matter what the curve is. And now you put an infinite attraction. This is the black curve in the reservoirs, and you get essentially the same curve. Actually, this is something which tests an old theory, which is called the Luther-Emery fixed point or the Luther-Emery liquid. And that's, again, something that could never be tested from the 70s and for which cold atoms provided a fantastic experimental system to test. Let me pass the spin transport. You can measure also spin transport and spin drag, or the Hall effect, which are very difficult questions. I just flash here a certain number of references for people who are interested. The Hall effect was another reason why Thouless got the Nobel Prize, because it gave this magic formula which allows to compute the whole voltage if you have a system in which you pass a current with a magnetic field. But this is all for non-interacting particles. And actually understanding the Hall effect for interacting particles is an extremely and deeply difficult challenge. So we are trying to play with this. We have several papers on this, but this is definitely something for which one is hitting a wall. And hopefully the combination of experiments and maybe numerics, analytics will help us to do some progress. And finally, let me conclude with one image, which is the dimensional crossover. We know the properties in 1D. We know the properties in 3D. What happens if we are somewhere in between? And for example, I showed you these organic conductors at the beginning, which are, I said, isolated chains, but they are not completely isolated. Particles can tunnel from one chain to the next, and that makes a mixture of 1D and 3D properties, which are at the source of this very unknown, for example, superconducting phase. So trying to understand how one can go from this physics, which is so peculiar to 1D, with deconfined excitations, with fractionalization between charge and spin, to the very conventional Fermi liquid properties in 3D, this is an open subject. And for that, clearly cold atoms where people can control the hopping between the tubes and so on should help us a lot to make progress on this field. I will just stop here, and I'll just conclude by this tour of one-dimensional physics by telling you that one thing that you should remember is that there is the equivalent of Fermi liquid theory in 1D, and that we have a framework which is a sort of bedrock on which you can study this physics, but of course on which you can go beyond. And the beautiful thing is that there are many, many challenging questions that are there that beg to be answered, which go beyond the simple physics of the Luttinger liquids, and which are both relevant for condensed matter and for cold atomic systems. The way to go is always now an interplay of analytical and numerical techniques, and of course, good ideas and great thinking to make progress. And if there is one thing that this field has taught, is that you cannot go with one side alone, but to make progress, you need both sides to really be efficient. And finally, there are many, many experimental realizations, both in condensed matter and in cold atoms. So when these systems are not freaks of nature, they are really deeply rooted in nature, and we need to really explain them. So I think this is just a very brief tour, but I would like to leave you at the end of this tour with this very nice Calvin and Hobbes cartoon, which I like a lot, which says it's a magical world, Hobbes' old buddy, let's go exploring. And on that, I stop, and I thank you for your attention.
Thank you a lot for a very nice talk. And I guess there will be many questions. Let me start out by asking first a question, and then again, I propose the following procedure for asking questions. Please write in the chat, something, and I will announce people in the order I see the messages, and there will be an opportunity to unmute and ask the question. But actually, exactly kind of linking to your crossover between dimensions, right? In 1D, there are these three beautiful vehicles. beta ansatz and conformal field theories and numerics, and seems like every wheel breaks already in 2 dimensions.
Yes.
And that cannot be a coincidence, right? So what goes wrong? You know, on one hand side, every wheel breaks. On the other hand side, right, somewhere far away in 3 dimensions, we await beautiful Fermi liquid theory where life is easy and, you know, nothing, you know, things kind of look almost trivial. So, you know, like just maybe a bit more philosophical question, right?
Yeah, so as you point out, in 1D we get this fantastic technique, the analytics, which is based on the fact that there are only collective excitations, of course, break down when you start coupling the chains. You can bosonize couple chains, but then you're dead into solving the problem. Beta ansatz fails, it even fails in 1D. There are many models which are not beta ansatz solvable. And numerics, when you start dealing with these couple chains, because the entanglement grows now much faster if you try to make the system as a snake 1D system, the computational time grows exponentially fast with the transverse dimension. So you hit the same exponential wall that you would hit by using, I don't know, quantum Monte Carlo or other methods. I think it reflects physics. I think it says that we have to deal with a physics which is different in 2D and in 3D than the 1D, but that the systems will remember that they come from a strongly correlated fixed point where spin and charge were deconfined and so on. So you can make progress, and actually a certain number of progress have been made by studying weakly coupled chains. And for example, for the Hall effect, this is what we tried. We tried to study not a 2D material, but to study several coupled 1D chains. And there it's still within the reach of the methods, as long as the number is not too large. So that's one route of attacking. And I think this route is having difficulties because when you go from 1D to 3D, you get many other excitations that appear than the collective ones. Unfortunately, it doesn't help to solve. So, but one can do a certain number of progress by dealing with quasi 1D materials. And there are good methods to treat this transverse coupling, at least approximatively, for spin systems. For example, RPA or mean field theory allows you already to do a very good job by dealing with this transverse coupling in mean field. But treating the 1D chains exactly. And then you can deal with a 2D or a 3D system in a pretty decent way.
Okay, thank you. I don't know, is there any questions from the audience? Let me ask maybe answer a quick question. And so in terms of Lagrangian liquids as a building block, so one impurity subdiffuses and does kind of suffer from a lot of slowing down. So what would happen if you start doing mixtures with, you know, maybe connecting it from weak, right, to more equal mixtures? Is there a complete theory or is there a good understanding of mixtures?
No, there is an understanding of mixtures, I would say 50-ish, which is 2-component Luttinger liquids, which people studies. But the point is that as the chemical potential of one of the mixture is getting lower and lower, then we are away from the applicability of the field theory method, for example. And when we study one impurity in the presence of the blue particles, we only apply the field theory to the blue particle, but we need to treat the impurity separately. Which means that it's a different way of treating it than the one we would use for the mixture. And how to go from one of these solutions to the mixture solution smoothly, nobody knows how to do it, except numerically, of course, because there you can put 1, 2, 3, 4 impurities without problem. But analytically, if we try to put many impurities by the method we use for the single impurity, it becomes very complicated very fast. And if we use the method for the mixture, it will get totally out of accuracy and reliability when the chemical potential of the red species will tend to zero. So again, we enter a no man's zone between 1 and 50%, which we don't know how to solve. So that's part of the challenges that remain completely open. And it's not innocent because, for example, we know this very deep connection that exists between diffusion and conductivity. This is Einstein relation. If I exert a force and I pull the impurity and it diffused when it was left alone, we know the mobility. But now, what is it when you get subdiffusion? Actually, there are beautiful experiments also in the group of Hans Christoph Nagel on a driven impurity in this very same situation, but this time you exert a force on the impurity and it has very weird behavior. Mm-hmm. So this is a very exciting type of physics that I guess people did not address before because these are very complicated problems and the motivation and experimental support was lacking. Now we have the motivation because experimental support and challenges exist. And unfortunately, or rather, I would say fortunately, we do have things to solve.
Sorry, may I ask a question?
Yeah, sure.
I mean, the chat was disabled, so I wasn't.
Sorry. Okay. But now I guess the audience is small enough that people can just unmute and participate in the discussion. Yes, please.
So my question is regarding this potassium rubidium experiment that you showed. And I remember the experiment, so yeah, I looked at it at some point, and it was very interesting, and you interpreted it as a polaron formation, right?
Yes.
And I remember that there was a discrepancy, like with the effective mass.
Yes,
can you comment on that?
Yes, I can, and I don't know whether I can even find the slide. So this is a polaron, but this is a weird polaron because again, okay, let's see if I have the slide here. Probably not. So let me go back to the original slide and try to comment. Yes, there was blah, 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 blah. Where is it? Out of equilibrium. Here it is. Okay. Okay, so what we did to deal with this experiment, the experiment was to release the blade, and then the wave function of the potassium was oscillating in the parabolic potential of the well, and we used the Feynman type variational method to compute the effective parameters of the theory, and it was working qualitatively but not so great quantitatively. And actually, there is a more recent paper by Astarachik and Eugene Demler, where they showed that if instead of the cutoff that we took in the field theory, which was a brutal cutoff, we said we get linear spectrum for the excitation, but we cut it at a certain momentum because there cannot be linear spectrum to infinite momentum. We take the Bogolyubov spectrum, which is linear at small momentum, but quadratic at larger momentum. Then actually the agreement becomes quantitative with the experiment. So I think it was simply because we were not treating well enough the high energy part of the experiment. And actually the same theory, the same way of looking at the problem, but putting a much better cutoff structure for the collective excitation of the bath seemed to have resolved most of the discrepancies that existed between the experiment and the theory. The experiment was also a little bit delicate because the point is that both the bath and the impurity were in the parabolic potential. So this affected the density of the bath. And there were several tubes with different densities. So that's one of the complications that cold atoms have, is that as long as they will not move to box experiments, the average is done over many tubes with many different densities. But to answer your question, yes, one can use polaronic techniques to study this type of problems. In that case, it was a Feynman variational method, but adapted, of course, to the 1D nature of the baths. It's not the 3D polaron. It's a 1D polaron, if you want. Call it as you want. It's a 1D polaron. But these techniques are pretty efficient to deal with this type of problems. There are other quantities we cannot use, we cannot describe with the same technique.
Thank you.
Can I ask a question?
Sure.
So you said at some point in the start that you combine all the methods like Bethe-Ansatz, numerics, and conformal field theory.
Yes.
You get better results.
Yes.
Is there any way to, combine them really, or do you just go to different regimes by different theories?
You should combine them, and let me give you an example here. For example, in this system that I showed, where I said one can quantitatively test the Luttinger liquid predictions, I have all these parameters here in this formula, which are the Luttinger exponent here, the velocity. I have the amplitude for the field, which has to be put in the field theory. Sorry, this one. This is the upper-fine coupling constant. Doesn't matter. And these parameters, you can say, well, I don't know them, but I know I have a power law, for example, and I fit and I see I have a power law with an unknown exponents. And computing these parameters analytically is practically impossible, because when I say analytically, I would say out of simple calculation is impossible, because you have to deal with a relatively strongly interacting system. But Bethe-Ansatz or numerics, in that case, it's a ladder, so it's not integrable. So numerics are extremely good in computing these parameters because they can do it out of short distance properties. So to get this agreement here, what we did, we used the field theory formula for the NMR relaxation time, but we fed in this formula the parameters K, U, and the amplitudes that were computed from the MRG using short distance correlation functions. So the DMRG was used in a maximally efficient way because it doesn't suffer from any finite size or need to go to finite temperature. We could do it with 0 temperature, short distance correlation, and it gives us with a very good accuracy, K, U, and the amplitudes. And then in our field theory formula, there is no adjustable parameter anymore. Before we could combine with the DMRG, we had all these adjustable parameters in the field theory, and then it's much more difficult to test because now you have to convince that you see a power law, but you don't know what the exponent is, and you know that you can fit practically a power law unless you get 1 or 2 decades with anything. So here we are not fitting anything. We are computing one curve and we are putting it on the top of the data. And the reason it was possible, and it was not, for example, possible here, you could say, why didn't I do the same thing for this power law? For this power law, I don't know very well the microscopic Hamiltonian, because what I have are electrons with a partly screen interaction, vibrations of the lattice, and so on. So there, it's simpler to say, okay, I have a power law, and okay, I will never be able to compute this power law from ab initio. What I can do is extract the power law from this experiment and then do another experiment where I'll get another power law and check that the parameter K that I put is the same in both. And that was done with transverse transport. But here we can do much better because for spin systems, we know the microscopic Hamiltonian. And therefore, we can do a DMRG calculation with the microscopic Hamiltonian, which is just an Heisenberg Hamiltonian with exchange here and exchange there that were measured by neutrons. So we don't have the exchange as adjustable parameters. And then the DMRG gives us K, gives us U, and we can inject in this pretty nasty formula to get what is the curve. So that's the way when I say you combined we combine the numerics and the analytics. In the sense, we either use the numerics directly to compute the correlation function if it's short distance or short time, but we can also use the numerics or the Bethe-Ansatz to get the parameters that we need to input in the field theory, and that makes the field theory essentially exact. Usually, field theory contains a lot of free parameters that you're unable to fix, not in that case. And I think that was one of the big progress that both numerical methods and the way to interface them with Bethe-Ansatz. And I must say this trick was originally proposed by Haldane. There is a very famous Haldane paper, not as famous as the paper for which he got the Nobel Prize, but another very famous Haldane paper, where he shows, he was having in mind Bethe-Ansatz and of course not numerics, but where he shows how you can extract these parameters out of thermodynamics measurement, which of course are easily accessible, and then inject them in the field theory.
Okay, thank you.
You're welcome.
If there are any other questions?
Yes, so if I may ask, so you mentioned you made the analogy between the situation that people were finding themselves in terms of the Landau liquid with technological applications then arising from having this kind of omnipowerful theory. So could you say a little bit more about kind of perspective, even directions towards technological applications of peculiar 1D or low-dimensional, strongly correlated quantum physics?
Well, my answer would be come back in 20 years, but no. For example, at the moment, a lot of people are playing with Majorana excitations at the end of chains, which are topological excitations. I would say the beauty of this is, I think, fundamental physics and trying to understand these excitations and so on. Now, there are people who would like to sell you this Majorana as ways to do quantum computing. And whether it will be a practical way to do quantum computing or not, frankly, I think today the answer is well, who knows? But definitely people are having this type of topological excitations in mind as possibility for building robust qubits or building robust components of quantum computing. Another thing that was more mundane was that people were saying at some point, oh, there are nanotubes. Nanotubes, now I think nanotubes, people would say it's a wrapped up graphene sheet, but they came before graphene. So, okay, nanotubes. Nanotubes are 1D wires, and we can maybe use nanotubes to wire very small structures. Well, if you want to use nanotubes as wiring very small structure, you'd better understand how they can transport things, because otherwise, you know, you're in for a bad surprise. So I don't know. If you ask me what is a killer application of 1D physics, I don't know. I would say personally, I don't care. In the sense that I'm excited by the, I would say, intellectual challenge and the fundamental aspects. Whether, for example, coupling 1D chain will provide also a reasonable route to understand physics pertaining to 2D and help solving 2D problems of correlated system, which people would say is, for example, the solution to ITC or things like this. I don't know, but that's certainly a route that one can follow. So I think we are, you know, if people had said the Fermi liquid theory was what will give you magnetoresistant, giant magnetoresistance, and then it will improve the magnetic recording in your iPods, I probably Landau would have said what? Okay, so I think I'm a little bit in the same situation here. If you ask me, I would say what? But I think it's a beautiful starting point to tackle strong correlations. And we are desperately in need of tackling strong correlations. That is definitely true.
Okay, thanks.
Thank you. So if I don't see any other questions, I propose...
May I, Maxime?
Sure.
Yeah, so maybe a naive question to get a feeling for what's going on when you go beyond 1D.
Yes.
So if you take the system of weakly coupled 1D chains, like in the organic superconductor, And then,
yes.
Yeah. And then, so naively, one could say we take the weak couplings between the chains as background and do a mean field theory on this. And then you get an effective 1D theory, but without particle number conservation.
Yes.
Which kind of 3D effects do you miss in such a theory? Or what would you lose?
Okay, that's a very good question. So depends on which system. If you deal with bosons or spins, you can do a mean field theory because an average of a spin exists or an average of a boson exists. And then indeed, you have to solve a 1D theory with either a creation operator or a spin S plus or a spin S minus. And this can be done. And for spin systems, for example, we used it and abused it. And I can probably even find a curve here. Let me show you this curve here. Here is the NMR that I already showed. Here is the TC, which actually I told you the ladders are weakly coupled, but not that weakly that there is not at some point a 3D order. And we can compute this TC by exactly the procedure you described, doing mean field. And again, the agreement is spectacular with the experiment. I could also show you, I won't do it because it would mean digging up in the slides. I could also show you other spin systems for which the agreement is much less good. Mm-hmm. And these are systems in which the J-perp is bigger. So for these systems, we need to go beyond RPA. If we want to do the spectrum, for example, of excitations, which is measured by neutrons, we have now such a good understanding of the spectrum of an isolated chain that we know that the mistake is not coming from our bad 1D susceptibility or response function, but is coming from the RPA approximation itself. And to go beyond this, your guess is as good as mine. What we started to do in the group is to couple structures like 3 chains coupled to 3 chains and only do the RPA in the coupling between this one. Of course, this is a technique that will become exact if I take 5, 7, 11, 13, but then we cannot do the DMRG on 5, 7, 11, 13. So the question is how fast this will give a good answer, and this is something we're exploring. But there is a system for which you cannot do that. It's fermions. Because for fermions, the average of a fermion operator is 0. I mean, it doesn't mean anything.
Right.
And so for this, this method is very inefficient. And you need to do things which are more sophisticated. And here is something we tried at some point with Antoine Georges, Silke Biermann, Sascha Lichtenstein, and Christophe Berthaud in the group, which was to do a kind of DMFT, dynamical mean field theory, where we would consider one chain and the rest of the universe as a bath. And then you have an incredibly complicated 1D theory to solve because particles appear and disappear, and solving it analytically is tough. Solving it numerically is tough. DMRG doesn't work because you need a time-dependent action, and DMRG doesn't work. So this is really where the challenge, one of the big challenges, how to deal with fermionic system, even in mean field, even in approximately treating the coupled chains. I can show you what it gives. It gives answers. We could get, for example, a 1D Fermi surface, which is lines normally, form pockets. So this is reminiscent of some of the things that happened with high TC and whatever. Okay, but this is a method which is really in its infancy and which is uncontrolled and which has a lot of problems. So this is a very good question. You put your finger exactly where the heart of the problem is. But even for spins and bosons, it's not so easy to do this mean field. And for fermions, it's a pure nightmare at the moment.
Yeah, thank you, Theirry.
You're welcome.
Can I ask you another question?
Sure.
So what you usually do is if you have a weak perpendicular coupling, you just couple through mean field, right?
Yes.
And then you do exact one dimension.
Yes.
But what if have you tried coupling it through, so instead of doing mean field directly on the Hamiltonian, you can do Schrieffer-Wolff transformation, 1 or 2 orders, and then do mean field on the effective Hamiltonian.
So as I said, we tried for the spin systems, we tried mean field, and this was not working too badly. But as I said also, and I don't think I have the curve to show it, it would be another, I would need to dig in another talk. We have simple enough, you see, that's the point. They are beautiful experimental systems, and people who do neutron, they give you the answer on what is the 3D susceptibility, what is the response, where are all the modes. And then you can check it doesn't fit with your mean fieldish thing. We didn't try, as I said, many more sophisticated methods. We tried this one, which was consisting in coupling exactly more chains and then doing mean field only at the edge. Maybe one can do Schrieffer-Wolff, which will bring a better starting point to do the mean field. I think that's exactly where people need to search and study. We can only try a limited amount of things, but that's where everybody is welcome to join the search. And of course, if one finds a good method, that's jackpot. Because I didn't show this compound. This compound, for example, is the compound from hell. It's Bakovo. It's made of spirals. I don't know. Yeah, here is the thing. It's spirals which are coupled in a squarish fashion. The 3D coupling is a nightmare. So RPA is working kind of, but this compound is beautiful. It has a double topological transition. It's fantastically interesting. And believe me, I would really give all the treasures of Switzerland. Well, I don't have them, so it's easy to give them. But to get a good method to deal with the 3D coupling in this one. What we did is the simple RPA, and again, it works not so badly, and so on. But yes, there are definitely other methods to couple chains to try, and but there are difficulties. For example, if you do mean field, what you realize is if you put a magnetic field, you mistreat the critical field of the system, the field at which the system is fully polarized. And now, which magnetic field should you put on your system? The one which is given by your mean field approximation, or the real one which is applied in the experiment? This is not innocent, because when you will compute the 1D response, it depends on this magnetic field. So again, I think your question is really where the research is. How to couple 1D structures, and what good methods to use. And as you know, people have also used methods like PEPs and methods which are directly targeted at 2D. But I think there is probably a way to indeed make progress on couple 1D structure, which will bring us to a 2D regime. But how to do it, if I knew, believe me, I would write it. So if you have good ideas, I can only encourage you. Go for it, test them, write them, publish them. I think it's exactly where the beef is exactly where the challenge is.
All right, I guess we had a very interesting discussion here, and thank you very much, Theirry, for
Thanks for
virtual visit. I hope again time will change.
Thank you very much, Maxime, again for organizing it. It was a real pleasure, not only the colloquium, but the whole visit. And thanks to all the people who asked questions and were there. I mean, it was as lively as a real live colloquium. So thanks a lot.